Hey there, welcome to this video about conditional GAN. So in the world of AI and machine learning, GAN are like magic. They help create super realistic data. Now imagine taking that magic to the next level with the help of conditional GAN. Conditional GAN is a type of machine learning model that goes beyond standard GAN by allowing user to influence and guide the generation of realistic data based on a specific condition or label. So in this video, we are going to use the TensorFlow framework to make our very own conditional GAN. So let's get started. So we will start by taking a look at the dataset itself. So the name of the dataset which we will use is called rock, paper and scissor. Here you can see we have paper folder, rock folder and scissors folder, and each of those folder contain the respective images. Here you can see few samples of paper image, then rock and the scissors. So we will use this data set for our conditional GAN. Now we'll start with the code. So first of all, we'll import all the required libraries and the functionality. And here you can see we are using TensorFlow, and rest of all are the functions which we will use to build our other helper functions. So now after importing all the libraries, we'll define some constants, that is image height, image width and number of image height is 100 pixels, image width is 150 pixels. Next again we'll build a function called create dir, and this function would help us to create a folder if that folder does not exist. Next we'll have a function called load image. So this function would take your image path, just a single image path and a single label. Okay, and so first of all we will read this image path. After that we will decode this PNG image. Next we are going to resize the image to the specific image height and image width, that is 100 by 150 pixels. Next we convert this this image tensor into float 32 specifically. Here we normalize the image, okay, by converting its pixel in the range of -1 to +1. So this is what we do. This is the normalization process, and at the end we give these two things, that is image tensor and the label back. Next we'll build our data set. Okay, so the name of the function is tf underscore dataset, and it uses tf.data API to build the training pipeline, and it takes images path. So images path is a list of all the images path, then images label, list of all the labels, and then a batch size. So first of all we take this TensorFlow.data API, then we have from tensor slices. So we give these images path and images label to this function. After that we shuffle the data set, that is these images and label. Then we use the map function, and here we load this load image function. So this load image, it take the individual image path and the label and pre-process it. Okay, after that we set some batches. We set a batch size, that is how many images would be in a batch. Okay, and then we have a prefetch. So prefetch is basically a simple functionality in TensorFlow which optimizes your training. So how it works, like let's say your batch number 1 is in training. So this what this prefetch functionality does, it makes sure that your second and third and all the other batches, how many it can afford to be in the queue, so that the next batch need not to wait. Next we'll build our generator, and this is an important thing because now we are working with conditional GAN. Okay, so let's get to the starting. So in the conditional GAN we take two things as the input. First is the noise and second is the label. So we have this function called build generator, it take your latent dimension, embedding dimension, and the number of classes. Okay, because here in this data we are using the class label as the conditional information. So what we'll have, we'll specify a given label and it would generate images for that given class only. So that is going to be our condition. So first of all, we have our input layer as noise, then we pass this layer via dense layer, and again we have a leaky ReLU activation function like what we have done in our previous videos. After that we have our second input, that is the label, class label. So class label would be an integer value, that is 0 1 2 like this, and now this label is given as an input to this embedding layer. Okay, and inside embedding we have defined the number of classes and the dimension of embedding. Now we flatten this embedding. Now we concatenate the features of both the layers, that is the noise and the label, and we concatenate them. And now onward we will have the single set of layer, okay, for this concatenated input. So it is followed by a set of dense layer which are followed by leaky ReLU activation function. So here you can see we have set the number of features as 512, then 1024, then 4096, and at the last the number of features are equal to image height multiply image width and multiply by number of channels. Again leaky ReLU as the activation function, and at last we reshape this feature map into a complete image. So that would be our image, and this x, that is this feature, would pass via this 10h and we get our final image. Okay, so this fake output we need to pre-process and we convert back it in the range of 0 to 255. So that is how we would get our image. Now we build our model. Our model take two things as the input. First is the noise, second is the label, and it gives you fake output as the output. So this is our generator. So again, in short, your generator take two inputs. First is noise, then a label, and give you the fake output. Now we'll build our generator. Note the generator, that is the discriminator. So here is the discriminator. So your discriminator take two parameter as the input. First is the embedding dimension and second is the number of classes. So first our input would be our image. This image can be fake or it can be real image. So we flatten this image and we have again a dense layer with 4096 as the number of features. It is followed by leaky ReLU and a dropout. And our next input would be our class label. This class label would pass via this embedding layer and we flatten it. Now we concatenate both the inputs. Okay, and after that it is followed by a series of dense layer, and after each dense layer we have a leaky ReLU and a dropout, and at last we have a dense layer with 1 as the feature. So why 1? Because the work of this discriminator is to classify whether the given image is real or fake. This is the work of discriminator. So here also our discriminator take two things as the input: our image, this can be real or fake, and then the label, and it gives you a prediction whether this given image is real or fake. So this is about our generator and this is about our discriminator. So we have built both the models, or you can say the neural network. Now we'll move on to the training process. Okay, so let me copy this entire function and I'll try to explain. So this is the name of our function, that is train step, and this entire function represent a single epoch, but all things happen in a single epoch. So first of all we take real images, a real label, then latent dimension, number of classes, generator neural network, discriminator neural network, and their respective optimizers. Next, we have a batch size, because in deep learning all the computation happen on batch size, okay, on batches. So first of all we need to calculate what is the batch size, because we require this batch size to generate our noise. Okay, so our loss in this would be binary cross entropy, really simple loss function. And next we will generate noise, that is a random thing. Okay, and the size of this noise would be batch size by latent dimension. So here you can see, this is why we require this batch size. Now we will first train the discriminator. So you can see we are training discriminator more as compared to the generator, because we want to make sure our discriminator is stronger than the generator, so it can force the generator to give more realistic samples. Now within this gradient tape, we first generate the fake images using the generator, and we give the generator the noise and the real images. After that, now we have both the real image and the generated image. Now we give real image and real label to the discriminator to get the real output. Okay, and then we give generated image and the real labels to the discriminator to get the fake output. And here we calculate the loss. So here we are using the binary cross entropy as the loss function. So this would be the ground truth for this respective prediction of the discriminator. So because this is real output, so the respective ground truth for this would be a same tensor. Same basically means a tensor with same height and width as this real output, but whose values are 1. Okay, and for this fake output, again it would be a tensor of same height and width, okay, but filled with 0. So you can say for real output the ground truth is 1, and for fake output ground truth is 0. We calculate our loss and we add both the loss, and then we calculate the gradient and apply those gradient to our discriminator neural network. Now we will move on to the generator. Again we use our generator neural network, give it the noise, real label, and get our generated images or the fake image. Now we give those fake image and the real labels. Okay, you can see in the generator we have given real label, so in the discriminator also we will give the same real labels, so that it knows, so that we can match those things, because our generated images would be based on these real labels only. So we give those generated images and real label to the discriminator and get the fake output. Now we calculate the generator loss. Here we have fake output, and now we want to make sure that these fakes are real. Okay, so due to that we give 1 as the ground truth. So you can see fake output, and again a function called tf dot once like. So what this function does, it takes a tensor and create a tensor of same dimension, that is same height and width, but whose values are replaced by 1. Okay, so again we calculate the gradient and apply those gradient, and this is how we get both the discriminator loss and the generator loss. Now we'll again have a helper function called save plot. If you have watched my previous video, you know this function. So it takes a few prediction or the generated images, epoch number and how many samples, and create a square map. Okay, let's say 10 by 10, and save those images. Now we'll move on to the main function. So here we'll define some hyperparameter. First is the batch size, that is 128, latent dimension 128, embedding dimension 128, number of classes third 3, number of epoch and number of samples. So we would generate 9 samples because we have 3 classes and then the path to the data set. Here you can see my batch size is 128 because I am using RTX 3090 which has 24 GB memory. So I can afford to use this much batch size. So maybe in your GPU you don't have that much memory to use that much batch size. So you can decrease it accordingly. So now let me run the GAN function. Okay, things are fine. Now we have the images path. Now what we need are labels. Labels list. Okay. So number of labels we're going to print, that is the length of labels list and the labels itself. So let me execute this. Okay, so number of labels, that is how many classes do we have, and name of each class is paper, rock and scissor. Now we need labels. So there's 4 line of code for that. So first of all, images label is an empty list. So now we're going to loop over images. Okay. So now what I'll do, I'll show you each of the thing. I need to explain things here, otherwise it would be confusing. First of all, what we'll do, I'll just print path and then break the loop. Okay, so this is the path. So first is the name of the folder, second is the name of that specific folder, that is the label. So this would be your label, and third would be name of the image. So what we need is this label. Okay, so now what we do, we split this label and we're going to print again, we're going to say print name. Now we have split this string based on those slashes, so it would give you a list. You can see list. First is the name of the data set, then this label and the name of the image. So this second item, you can say -2. Now you may imagine why -2, why not 1? Maybe your initial path can change, but any path you give, this paper, this class label would be second last. So this is the first class, this is second last. That is why I use -2. Now we find the index of this label from this labels list. Remember this labels list? I find the index using labels list dot index and the name. So if that specific label is present in this list, so it would give you a specific index. Okay, so you can see the name of the class is paper, and this item is present in this labels list and at the index 0. So this would be our label for this respective image. So this is your real image and this is your real label. Now what we do, we append this index to this image labels list. Now we have both the real images and the real labels. So let me print the length to make sure both of them are same. Okay, you can see both the images list and the labels list have equal number of items. Okay, now we're going to create some folders. Okay, so we have used our create dir function to create a folder called samples. In this folder we would save the predicted image, not the predicted technically, the generated images which are generated after each epoch. And in the saved model folder we would save the weight file of both the generator and the discriminator. Here are your generator neural network and the discriminator neural network. Now what we'll do, we'll print their summary. Just to check whether these are working fine or not. If they're not working fine, they would drop an error. Okay, so first of all, we have generator. You can see all the layer, their shape and everything. Also the number of parameters they have. So things are working fine till here. Now we would start with the training process. So first of all, we'll define the optimizers for both of them. That is the discriminator and the generator. Next, we would prepare our images data set, that is the training pipeline. Then we would add this seed or the initial noise. So this noise would remain fixed during the entire training process, and we're going to generate samples from this noise, and its the dimension are number of samples, that is we say as 9, can see, and the latent dimension. Now we also need the labels. So if you see, we have 9 samples. Okay, it would be like 0 0 0, then 1 1 1, then 2 2 2, something like that. So what I've done, I've repeated this process. For item in seed class label, so it would be first item would be 0, then seed label would be 0 plus equals to item multiplied by 3. So it would be like this list contains 0 and it multiply 3 times. So this would repeat it 3 times. It would be 0 0 0 and then 1 1 1 and then 2 2 2. So the final seed list would be like 0 0 0 1 1 1 and 2 2 2. Let me print it for you so that you can also see. Okay, should be seed label, not seed class label. Sorry for the mistake. Okay, 0 0 0 1 1 1 and 2 2 2. Really simple. Maybe you can manually also do it, but I like to do things programming way. And as a programmer, you might feel this thing that as a programmer, what we like to do, we like to automate or like to write code for 2-second thing. Okay, and that 2-second thing take 2 minutes. This is kind of, what do we say, a thing in programmers. Okay, now we'll go to the main programming part. Okay, so now we'll start a for loop. That is, this for loop would run this much time, that is number of epoch, that is 1000 time. We'll start a time here just to calculate how much time an epoch take. Then we have two empty variable, that is dlos and glos. Now we'll loop over the image data set, and within each iteration it will give a batch of image and batch of label. Now we use our train step. We have our batch loss and we sum those batch loss. After that we calculate the mean. We have mean loss. Then we save our weight file. Okay, now we use our seed noise and the seed label to get our fake images. Okay, these are example, and we save those fake images. And here we have the how much time is taken in this process, and we print the current epoch, number of epoch, time taken, and both the losses. So this is how it would work. Let me train this for a few epochs and then we'll see how it looks. So let's just wait, see if it would it run or it. Okay, you can see it start running. So this first epoch take 10 seconds, and this is our discriminator loss and then generator. So ignore this warning from TensorFlow. If you have any solution, you can solve them. Otherwise, in my case, these are fine. So now we have two folders, that is sample. You can see samples are being saved, but for now you cannot see anything. But in the last 6, you can see something kind of green in the background, and then the blue something kind of blue. Okay, now we can easily see that this is some kind of hand, human hand, because the dataset contain human hand. Now the second folder, saved model, contain both the weight file, that is discriminator weight file and the generator weight file. Now let's work on the test. This test would help us to generate images. So first of all, we'll import all the required libraries and functionality. Next, we would have our save plot function. Again, it would help us to save those examples in the form of a square. Now let me copy paste the entire code and I'll explain to you the main part. So first of all, we'll have some hyperparameters here, that is how many sample we want to generate. So this should be a square number, that is 4 by 4, 5 into 5, because the plot would be generated from a square. That is how I have programmed it. Then latent dimension. So this latent dimension and embedding dimension should remain same as what is specified during training. See here, latent dimension and embedding dimension. Then we load our generator neural network. Next, we have some latent point, seed or noise. Again, same seed class label. Next, we give those latent point and the seed label as the input. We generate some synthetic images and we save those. Okay. So I've stopped the training part. Let me show you the samples, the last sample. Okay, you can see it starts generating some figures. So let's just use that weight file only just to check. Okay, so it has generated fake sample. Okay, so these are some of the, these are 9 images you can see from 3 different classes. Okay, so the sequence would be something like, let's go back, it would like paper, rock and scissor. So it should be PRS. Now what I'll do, I've already trained this. Okay, I'll delete this folder and I'll replace them with mine. Okay, so what I'll do, I'll give you an idea how the generated samples look during training. So if you remember the sequence, paper, rock and scissor, and just take a look at this. I think I've trained it for 500 epochs. Yeah, I think the scissor is really working, but and both the classes are also working, but the third one is really looking nice because we are using dense layer. This is why it is not that much clean. But if we use, okay, this is the last, okay, this is the 500. Now we have our train weight model which is trained till 500 epoch, and I think there's no point. Okay, and this thing usually happens when I replace weight files from the same architecture. Okay, let me check it and come back. Okay, I'll post the video here. Okay, so I've tried everything to solve this and nothing works. So if you have any solution to this, then please do me. So what I've done, I've trained it again for about 200 epoch and then tested it, and it finally worked. I don't know why, but it worked. So let me just show it to you also, and please don't have any error now. And I think it might be due to these errors which are coming. I think I need to work on them. Okay, so here's how these generated images would look. So first is this paper, then rock, and then scissor. So let's do it again. Okay, now let me. Okay, again, paper, rock, scissor. You can see these are fine, but if you replace your dense layer with a with convolution layer, the performance would be much better. But that content would be for a next video. So I hope you learn something useful from this video, and if you really did, then please make sure to like this video and share it with your friend. So thank you, have a nice day.